Okay, so you're doing antiderivatives and indefinite integrals. Why not pause the video right now? Well, not yet. And try to work each one of these, and I'm going to give you the answers. And so unpause it when you get finished and you'll see the answers. So go. I hope you paused it, and now here's the answers. So what I would do is I would work through each one of these and make sure you know how I got my answers. Probably this last one gives most students a hard time, but notice if you separate this into two fractions, actually this x to the fourth, these cancel, and then I end up with just a minus 5 over x, and that's how I get this. Here's also a practice problem. So pause it and work it, and then come back for the answer. Did you get approximately 12 months? If not, let me know and we'll work it together. Let's keep moving right along. This is called the fundamental theorem of calculus. Before we look at that, if you remember in the last video when we were doing substitution, I said this is kind of weird in this chapter. They give you this problem to substitute because you don't actually have to use substitution, meaning there's a shortcut way to do it. And so that's what this is the shortcut way, because you know the antiderivative of e to the x is just e to the x, because if you take the derivative of e to the x, you get e to the x by. Well, if you have another value up here to find the antiderivative, you just simply rewrite e to the whatever and then 1 over this constant that's out front. And so it's a nice little shortcut way to be able to not have to go through and use substitution. So let's say, for example, I have e to the 4x dx. Well, it would be e to the 4x and then 1 over the 4. And of course, I could check it and see that I do get back my e to the 4x. Let's see an example where daily cost is given by this function. We have a domain. Marginal cost then would be 180, right? Because you take the derivative of cost to get marginal cost. What is the change in cost as production is increased from 5 units to 10 units? Well, we could take our function and we could subtract. So we plug in 10, we plug in 5, and we subtract the two values. And I get 1800 minus 900. If you notice, if I factored out a 180 here, I get some number and that 10 minus 5 again. It's going to become important. And so I can see that I could get the change from 5 units to 10 units. And so this is the key part right here, is I'm looking at this increase from 5 to 10 units. Well, if I could figure out how to get this value, I wouldn't even have to go through this. Well, if we look at the actual graph of this, we can see that if we're looking at this change here, okay, from what we just found, the C10 minus C5, what happens is this, of course, is constant, okay, meaning our slope is constant. We'll look at what the slope is. That was at 180. And so if I graph the slope and I wanted to find the area underneath this line, well, if I shade in this area, I have a rectangle, and I would simply take the height, which is 180, times the width, which is 5, because 10 minus 5 is 5, and I get that answer. So what you're going to see, what we're going to be doing here, is we're going to be finding area. And you might say, well, what's the big deal? I can find the area of a rectangle. Well, what if you have a function that looks like this, and you want to find the area underneath it to get, say, total costs between, now this is 5 to 10 days. Well, because this isn't linear and constant, then we need another way to do this, and that's what you're going to find out is the fundamental theorem of calculus. All right, so here is my integral notation. The difference here is you see these A and B, where what these are the lower and upper limit of my integration. In other words, this would be 10 and this would be 5 on my last example. Everything else in here stays the same. I still have my function, I have my variable of interest for my integral, I have my integral sign. So what we're going to end up doing, this fundamental theorem of calculus says, if I find, because we just said if we had this slope here, we just saw that it was the slope times the difference. If I could find my original function, my antiderivative, then I could simply evaluate at these limits of integration. And so with the fundamental theorem of calculus, we can easily evaluate area underneath the curve. And again, who cares about area underneath the curve? Well, that could be something like total cost, like our previous example. There's different properties. So for example, if I had a zero width interval, hopefully that would make sense to you. If the width of this is 0, then the area would be 0. The constant multiple, which just says you can pull a constant out front, but when you multiply a constant by an area, it just adds more area. If you want to sum two areas, so that's all this is saying here is I have one area of one function, one of another. I can add the two areas. And this one's nice because sometimes you might want to break down from A to B and B to C, or of course, as long as this is continuous, you can go all the way from A to C. All right, so as you can see, we're doing the same thing that we did when we had an indefinite integral. An indefinite integral didn't have these limits of integration. Now we're doing a definite where we're actually finding area. So the first thing we do is we find the antiderivative. And I know that antiderivative because I've been practicing these is ln of x. And now I'm going to just simply plug in where I see an x, a 2, minus, I'm going to plug in a 1. And that's what this says to do here. So I plug in ln of 2 minus ln of 1. I stick it in my calculator and I get this answer, which is the area. So the key here is this is the area of my function from 1 to 2. And this is important that you're understanding that that's what you're doing when you evaluate, you plug in these limits, is you're finding the area underneath the function. So let's look at another one. I first just look at this, I find the antiderivative. So 6x minus x to the 4th over 4. Now I plug in these values. So I plug in 3, I plug in 2. You always plug in the larger value first, because if you think about it, if you're trying to find distance, if you had something like this and I wanted to know what the distance from 2 to 3 would be, you wouldn't say 2 minus 3, because that'd give you a negative 1. You'd say 3 minus 2, and that would give you that distance. So that's why you want to be sure the larger value is always evaluated first. And so I plug it into my calculator and I get it. Now my question would be, why is it negative? How could I have a negative area? Because area, I'm shading in something. It sounds to me like area should be positive. And this is where I tell students that really understand what they're doing, they graph. Graph this. And you can see why it's negative because it's below the x-axis. Okay, so you could get negative area if part of your function, or in this case, all of it, is below the x-axis. Look at another one, find the antiderivative. So antiderivative of 2x is x squared, 3e to the x is just 3e to the x, minus 4 ln of x. I plug in 2, I plug in 1, and I get that in my calculator, and I look at the graph to see what it looks like. Okay, so again, I'm taking this function, which is here, And then I'm just drawing lines straight down to show you that I'm shading in this area. An amusement company maintains records for each video game installed in an arcade. Suppose that C of T and R of T represent the total accumulated cost and revenue in thousands of dollars, T years after a particular game has been installed. Suppose also we have marginal cost and marginal revenue. The value of T for which marginal cost equals marginal revenue is called the useful life of the game. I want to find the useful life of the game to the nearest year, and then find the total profit accumulated during the useful life of the game. So let's find the useful life of the game to the nearest year. I set these equal to each other. I'm going to solve for T. So this was the step we did in the last lecture where we said, how do you solve when you have a variable up in the exponent? You take natural log because that's E, base E. And so this, of course, brings this down. The ln of E cancels out. I divide both sides by negative 0.5, and I get my answer. So I get approximately 3 years. Find the total profit accumulated during the useful life of the game. Well, then I need the actual profit function to find total profit. And we said the useful life was up to 3 years. So this would be from 0 to 3. I take this and I find my antiderivative. And I plug in my values and just throw all that in your calculator. And remember, they said this was in thousands. So again, what you're finding is the area underneath this curve. So you're still doing the same thing with finding area. We can also use definite integrals for average values. If you think about how do you find an average, you take a total and you divide by the number of units, right? Your total, add up all your grades and divide by how many grades you had. Well, we said what we're doing here is we're finding a total. So here we're going to divide by that distance, okay? So in other words, however many units. Do this part first and then divide by whatever your B minus A is. So it says the total cost in dollars of printing X dictionaries is C of X equals 20,000 plus 10X. I want to find the average cost per unit if 1,000 dictionaries are produced. I want to find the average value of the cost function over this interval, so from 0 to 1,000 dictionaries, and then write a description of the difference between these two. Well, the first part just says find average cost. Well, average cost is the cost divided by the number of units. So in this case, my average cost is going to be 20,000 plus 10x divided by x. And so I just canceled out the x's, 10x over x. I want to know what the average cost per unit for 1,000 dictionaries. So I plug in 1,000 and I get my average cost. I want to find the average value. So in this case, I'm using this function. Once again, I have my cost function here. So I do this piece first. I find the antiderivative. How is this 1,000? Because it's 1,000 minus 0. And then I evaluate at these points. And finally, I divide by 1,000 and I get 25,000. So what's the difference? If you just do the setup for printing, it costs 20,000. Okay, so in other words, your cost of printing 0 dictionaries, just setup cost. If you print 1,000 dictionaries, it costs 30,000 because it's $30 per dictionary. If you print some random number of dictionaries between 0 and 1,000, then on average, it costs about 25,000. Actually, these numbers really don't, there's nothing to analyze here. One was just giving me my cost per dictionary, where this one I was going to get an average cost.